All right, so we're talking about linear programming. I'm going to go a little slower on this one because I know it was giving some of you some issue. So, presented on the screen is a problem, and it's going to say you're buying filing cabinets. You know cabinet 1 costs $10 per unit, requires 6 feet of floor space, and holds 8 cubic feet of files. Cabinet 2 costs $20 per unit, requires 8 square feet of floor space, but holds 12 cubic feet of files. You're giving $140 for this purchase, though you do not have to spend that much. The office requires no more than 72 square feet of cabinets. How many of each cabinet should you buy to maximize storage? All right, so now we have to set up our system, right? So first things first, it's a word problem. What do we do with word problems? Set it up. So, or we define our variable. And that one's, all right. X is going to be equal cabinet 1. Y is equal cabinet. Okay. So, have that set up. Now, we need to set up a system of linear inequality. So, we have to ask ourselves, what's our constraint? What's stopping us from going on to infinity? First, we have cost, right? Said we have $140 max. So we have to say 140, something needs to be less than or equal. So what needs to be equal? Well, the cost of cabinet X and the cost of cabinet Y added together needs to be less than 100. So I can say X plus Y less than 140. But X and Y are the number of cabinets, right? So I need to give it some value. This is a value. This is dollars. What's X worth in dollars? Well, if we go back to our problem, we can see each one is $10. Our Y, each one worth $20. Okay? Now our system's starting to take shape. Add a second constraint. What was that constraint? It was volume, right? We had so much square feet. Or I'm sorry, not volume, space. Volume. We had only so much square feet. How much square feet did we have? Well, it was 72 square. Okay, so we have to be less than or equal 72 square feet. Now we ask ourselves once again, all the cabinets of X and all the cabinets of Y have to be less than that. Well, what's their coefficient? How many square feet they took up. X was 6 square feet, Y 8 square feet. 2 more constraints, and they're implied. What are they? Y is greater than or equal to 0. X is greater. I've already shown that by having just quarter 1 be my. So, or quadrant, sorry. All right. Now I graph them. So I'll do this one in blue. So I'm going to use the intercept method. Do that. Remember, we cover up the 1. 20y equals 140. That's the same as 2y equals 14. So y is going to be 7. X is 0. 1, 2, 3, 5, 7. Cover that up. We get x is 14. 11, 13. Okay. I'm going to connect them with 9. And we said that it's less than, so I'm going to shade below. I'm just going to put a tick mark right. Okay. Now, I'll do the second one in red. Same thing, going to use the intercept method, right? Let's find y. Cover up x. I get 8y is equal to 72. So it's 9, right? 1, 9. Cover up y. I get 6x less than or equal to 72. That's going to be what? 12? 12? Or, yeah, 12? 5, 6. 1. 12 is that. True. Right. And then connect those lines. Once again, it says less than, so I'm shading below. This area here, my feasible. And now have 1, 3, 4 vertices. I need to find those vertices. How do I do that? I set up a system equation, okay? So this one, I can just count, right? So it's 1, 2, 3, 4, 5, 6, 7. My first vertex right here is going to be at 0. This one, 0, 0. This one, 1, 2, 3. Very nice. All right? You can count if you want, but I promise you that's 12. This one, on the other hand, I need to find. I find that by setting up a system of equations using these intersecting lines. I technically did that for these two, but it was easy enough because it's just 0, 0. Or, yeah, x is 0, y is 0. So, I'm going to set up a system of equations over here. We get 10x plus 20y is 140. I get 6x plus 8y equals 72. I'm going to solve that with substitution. I'm going to solve for x up here. I get 10x is equal to negative 20y plus 140. X is equal to negative 515. Okay? Take that, plug it in there. 6 times negative 2 is negative 12y plus 14 times 6 is going to be 26. Nope, 80. 10 times 80. All right. 84 plus 8y is equal to 72. And negative y is equal negative 12. Y is equal. Okay, so now I know my y value is 3. I then take this and I plug it back in up here. So I get 6x plus 8 times 3, 72. 6x equals 8. Right? This ordered pair, 8, comma. Yep, looks good. All right. So I've successfully found all 4 vertices. Last step is to find my objective function. This is the thing I'm trying to maximize or minimize, right? We look back at the problem, we're trying to maximize our volume, right? We need to maximize our volume. So, set that up. volume, our total volume, don't know yet. Don't know what kind of cabinets we're going to buy. But we know it's going to be total volume. Volume, or volume of our cabinet X, or volume of cabinet Y. Okay? Now I just got to fill in those coefficients again. So we look back at our problem. When it talked about volume and cabinet X, what did it say? Well, each one holds 8 cubic feet of files. Talked about Y, each one holds 12 cubic feet of files. Now I need to plug in my 4 vertices, figure out which one maximizes the space. So B 0, 0 equals 0. B of 0, 8 equal to 12 times 8 is 96. All right. Here, volume B 12 equal 8 times 12. That's just going to be the same thing. Cubic. And finally, B 8, 3. That's going to be equal to 8 times 8, which is 4, plus 12 times 3. All right. Now we're trying to maximize. So finally, we look at all of our points. Which one maximizes our volume? Well, it's this one. Oh my goodness. I missed a huge step. What's that? It's label my graph. So, don't forget to label your graph. So we have number of cabinet 1s and number of cabinet 2s. Okay? So, have all that. I've figured out maximize volume, I should do that. Now it's a word problem, so our final answer is in sentences. So it's to maximize volume, company should buy, then said 8, 3, each cabinet 1, 8 of 1, and 3. And that is our final solution. Okay? This in blue is our final solution. Point is, you gotta get 3. Find these. We're looking to maximize. Have to answer that question. I said, what am I trying to maximize? Or how do I maximize? Well, to maximize, company should buy this and that, okay? So again, to start from the beginning real fast, find your variables. Decide what your constraints are. What's restricting you from going on to infinity? In this case, it was price. We only had $140. Volume, we only had 72 square feet of area. Stop saying volume. Can't have negative numbers, so that constrains us. We then graph that, shade it in, and find our feasible region. This shaded triangle-ish looking thing. We then find our 4 vertices. Those 3 are easy. This one, we have to set up a systems of equations. I solved using substitution. You can use elimination. Doesn't matter. Once you have all 4 vertices, but there might be more. You might have 5, 6, 7. Depends on how many equations you have. You have left. You have 3, right? So once you have that, you then find your objective function. So you go back into that word problem and say, what am I trying to maximize or minimize? It specifically said in the problem, you need to maximize the number or our volume stored, right? So I read volume. I went back. What does volume have to do with anything? Well, it said there's 8 cubic feet for cabinet 1, 12 cubic feet for cabinet 2. That's my objective function. The total volume is the volume of each type of cabinet put together. Took those, plugged in all 4 vertices, and found that that gave me the greatest volume. That's what I'm looking for. That's my final solution. And I write it as a full sentence. If you do not write full sentences, I will take off end of line. All right? So hopefully this helped. This is nice because it's a review of all the previous chapters. Graphing linear inequalities, solving systems of equations, and word problems. So we combined all of them in one lesson. So get this one, you're going to be doing great for all the previous 5 chapters. All right. Hopefully this helps. Go on to the next lesson.